A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
Hi Herman and Corin. So I was listening to the episode about guanfacine's use in ADHD. It was a really fascinating episode. Shone a lot of light for me on off-label prescribing. I have to admit I definitely always assumed it was some kind of a dubiously legal practice, which I guess in retrospect makes absolutely no sense, given that no doctor is going to risk their license just because they want to try a drug for a patient, just being realistic. So it's good to know where it stands and really interesting to know about the mechanism of action. It was actually so interesting that I have just one more prompt, one more question. How many times have you heard me say that? We talked about Singulair before. Singulair being a trade name for montelukast, a leukotriene antagonist, leukotriene receptor antagonist, if I recall correctly, and how that drug works. And this is kind of the classical drug associated with allergic asthma. I've always wondered why it is that that's the case and why antihistamines don't have a greater role to play in asthma management, because that seems like the allergy thing. And then I get to thinking, well, what's the difference really between allergies, if that affects your breathing, and asthma? Now I have asthma and I've always just kind of put it alongside allergies as this kind of cascade of not feeling great, and whatever I'll take to make it better is welcome. But I'd be interested to know why it is that leukotrienes are so specifically associated with airway inflammation in asthmatics as opposed to histamine, which seems to have a more generalist effect. And is it commonplace for asthmatics to actually take these? The other question I have, Herman and Corin, this brings me way back to a time when I used to spend afternoons with a very interesting medical student. A story for another day. And he was explaining a bit about the about how all these things work. And I remember that there is a allergic inflammation is a cascade. This concept of the inflammatory cascade, that one thing triggers another. And when we're looking at histamine or leukotrienes, we're looking at various mediators in that cascade. Now my question was, why can't we just go upstream instead of targeting these specific molecules that are involved to greater or lesser extent in different conditions? Even if we were able to identify medicines for each specific type of inflammation, you can't tell someone take these 10 pills every day to keep your allergic asthma under control. I recall the answer being something like that. There are these upstream drugs, but really for very, very severely asthmatic people. Think the type of folks that are in wheelchairs and literally very debilitated by the disease. And they're also extraordinarily expensive. Very interested to know, Herman and Corin, on why, what role histamine plays in asthma, why it is that leukotrienes are very much associated with it, and what progress is being made in the field of treating this, that instead of maybe looking at these chemicals, we're trying to find the more effective upstream targets. Over to you two.
Alright, we're back. And today we are diving into a topic that hits home for a lot of people, including our friend Daniel, who sent in today's prompt. Daniel has been thinking about the mechanics of asthma and allergies, specifically why we use certain drugs like Singulair for one and antihistamines for the other. It is a question that sounds simple on the surface, but once you start pulling the thread, you realize you are looking at one of the most complex systems in the human body.
Herman Poppleberry here, and I am ready to get into the weeds on this one. Daniel mentioned listening to our episode on guanfacine and ADHD, which led him down this rabbit hole of off-label use and specific mechanisms of action. It is a great starting point because the way we categorize these conditions often hides the fact that they are all part of the same complex biological symphony, or in some cases, a very loud and uncoordinated garage band. We tend to put diseases in boxes, but biology does not really care about our boxes.
Well, before we get to the biology, I have to say, it is good to hear from Daniel. I hope things are going well over in Jerusalem. He mentioned his own experience with asthma, And it is a perfect example of how personal these medical questions can be. It is one thing to read a textbook, but it is another when you are the one reaching for an inhaler in the middle of the night. Daniel is an automation and AI guy, so he is used to looking at systems and flows, and he wants to know why the code of our immune system seems to have these specific frustrating bugs.
And he asks some really sharp questions. Why is histamine the star of the show for hay fever, but leukotrienes take center stage for asthma? Why can't we just move upstream and shut down the whole process before it even starts? These are the kinds of questions that pharmaceutical researchers spend decades trying to answer. To understand it, we have to look at the geography of the human airway.
So let's start with the basics. Most people think of allergies and asthma as two separate things. You have your itchy eyes and runny nose for allergies, and you have the tight chest and wheezing for asthma. But Daniel noted that they seem linked. How do they actually differ at the cellular level? Are they just different versions of the same mistake?
That is the right place to start. If you look at the big picture, both are overreactions of the immune system. They both fall under the umbrella of what we call type 2 inflammation. Imagine your immune system is a security team. In most people, the team ignores things like pollen, cat dander, or dust mites because they are harmless. But in people with allergies or asthma, the security team sees a grain of ragweed and decides it is a high-level threat, like a viral invasion.
Right, so the initial trigger is the same. An allergen enters the body, the immune system freaks out, and it starts a reaction. But why does that reaction look so different in the nose versus the lungs? Why does one make me sneeze and the other make me feel like I am breathing through a tiny straw?
It comes down to the specific mediators released and where they act. When that security team decides to attack, they use different weapons for different environments. Think of the mast cell like a tiny biological grenade. These cells are packed with chemicals, and when they are triggered by an allergen, they degranulate, which is just a fancy way of saying they explode and release their contents into the surrounding tissue. But the tissue in your nose is very different from the tissue in your bronchioles.
And that is analogy number 1 for the day, folks. The mast cell grenade. So what is inside the grenade? And why does the explosion cause such different damage depending on the room it goes off in?
Inside that grenade is a whole cocktail of things. You have histamine, which is the most famous one. You have proteases, you have cytokines, and then you have the lipids, which include the leukotrienes. Now histamine is very fast. It is preformed and stored in those little granules, so the moment the cell pops, the histamine is out there doing its thing. It makes your blood vessels leak, which causes swelling and a runny nose. It hits nerve endings, which causes itching. In the upper airway, the nose and eyes, that is the dominant player because those tissues are mostly about blood flow and mucus.
Okay, so if histamine is so fast and effective at causing trouble, why isn't it the main problem in asthma? Why don't antihistamines work for an asthma attack? I have tried taking a Benadryl during a tight chest moment before I knew better, and it did absolutely nothing for the wheezing.
That is the million-dollar question. Scientists actually tried using antihistamines for asthma for a long time, and the results were always disappointing. The reason is that the lungs are a very specialized environment. While histamine can cause some bronchoconstriction, which is the tightening of the airways, it is relatively weak in that department compared to leukotrienes. Your lungs are wrapped in smooth muscle. When that muscle contracts, the airway narrows. Histamine just does not have the grip to keep those muscles clamped down for long.
How much weaker are we talking about? Is it a small difference or a total mismatch?
It is staggering. Some studies suggest that certain leukotrienes, specifically the cystinosyl leukotrienes like LTD4, are 100 to 1,000 times more potent than histamine at causing the smooth muscle in your lungs to contract. So even if you block all the histamine with a drug like Claritin or Zyrtec, the leukotrienes are still there, and they are doing way more damage to your ability to breathe. It is like trying to stop a flood with a paper towel while the dam has already burst.
1,000 times more potent. That puts it in perspective. So while histamine is making your eyes itchy and your nose run, the leukotrienes are the ones actually slamming the doors shut on your airways. They are the heavy hitters.
And it is not just the tightening. Leukotrienes are also responsible for a lot of the long-term misery in asthma. They increase mucus production, which plugs up those narrowed airways. They also act as a chemical signal that calls even more inflammatory cells to the lungs, specifically eosinophils. This creates a cycle of chronic inflammation that thickens the airway walls over time. This is why drugs like Singulair or montelukast are so important. They are leukotriene receptor antagonists. They sit on the lock so the leukotriene key can't get in and start that whole process of tightening and mucus production.
We actually talked about the timing of Singulair back in episode 617. It is not a rescue inhaler. You can't take it and feel better in 5 minutes because it is working on that underlying process. It takes a couple of weeks to really stabilize the system. It is more like a preventative maintenance routine for your lungs.
Right, and that brings us to Daniel's second big question, the cascade. He mentioned that inflammation is a cascade, and he is absolutely right. The inflammatory cascade is like a series of falling dominoes, and that is analogy number 2. Once the first domino falls, it triggers a whole sequence of events. By the time you get to leukotrienes, you are already several dominoes down the line.
So if it is a sequence, why are we targeting the last few dominoes? Why are we blocking the leukotrienes at the very end of the line instead of stopping the first domino from falling? If we could stop the first one, wouldn't that solve everything?
This is where the biochemistry gets really interesting and really frustrating. The further upstream you go, the more essential those processes are for your actual health. You don't want to shut down your entire immune system just because you are allergic to dust mites. You need your immune system to fight off viruses, bacteria, and even cancer cells. The first dominoes are often shared by many different systems.
That makes sense. It is the classic side effect trade-off. If you use a sledgehammer on the whole system, you fix the asthma, but you might end up with no defense against a common cold. It is like turning off the electricity to the whole house just because one light bulb is flickering.
Let's look at where leukotrienes come from. They are part of the arachidonic acid pathway. Arachidonic acid is a fatty acid found in your cell membranes. When a cell is triggered or damaged, an enzyme called phospholipase, A2, breaks that acid loose. From there, it can go down 2 main paths. One path uses the COX enzymes or cyclooxygenase to make prostaglandins. These are involved in pain and fever. This is what aspirin and ibuprofen block.
Right, we know those well. But wait, if aspirin blocks one path, does that affect the other? Because if you have a fork in the road and you block one side, all the traffic has to go the other way, right?
You nailed it. This is actually a really important point for asthmatics. In about 10% of people with asthma, if you block the COX path with aspirin, all that arachidonic acid gets shunted down the other path, which uses the 5-LOX enzyme or 5-lipoxygenase. This path leads directly to the production of leukotrienes. This is why some people have aspirin-exacerbated respiratory disease, or AERD. They take an ibuprofen for a headache, and it accidentally triggers a massive production of leukotrienes, leading to a severe, life-threatening asthma attack.
That is a terrifying side effect. It shows how interconnected these pathways are. You think you are treating a headache, and you end up closing your lungs because you diverted the biological traffic.
It really highlights why targeting the source is so hard. If you try to block the enzyme right at the top, like 5-LOX, you are messing with a lot of different biological functions. There is actually a drug called xylitol that does exactly that. It is a 5-lipoxygenase inhibitor. It stops the production of leukotrienes at the source rather than just blocking the receptor like Singulair does.
So why isn't everyone on xylitol? If it stops the production entirely, wouldn't that be better than just blocking the receptors?
You would think so, but it is a tough drug to take. It can be hard on the liver, so you need regular blood tests to make sure you aren't causing permanent damage. It also has to be taken 4 times a day in its immediate release form. Compared to taking 1 pill of Singulair before bed, it is just not as practical for the average person. So for most people, blocking the receptor is the sweet spot of effectiveness and safety. It is a more targeted strike.
Okay, so that covers the middle of the cascade. But Daniel asked about going even further upstream. What about the very beginning? What about the signals that tell the mast cells and the eosinophils to start acting up in the first place? Before the arachidonic acid even gets involved.
That is the cutting edge of asthma research right now. We are talking about biologics. These are drugs that target specific proteins called cytokines. Think of cytokines as the radio signals the immune system uses to coordinate an attack. In the type 2 inflammatory response that causes asthma, there are a few key signals: interleukin-4, interleukin-5, and interleukin-13. These are the generals giving the orders.
I've heard these names coming up more often in medical news. These are the ones that tell the body to produce IgE antibodies, right? The wanted posters of the immune system.
IgE is the antibody that specifically targets allergens. It is like a wanted poster that the immune system puts up. Once an IgE antibody for pollen is made, it coats the mast cells. The next time a pollen grain shows up, it binds to that IgE, and that is what pulls the pin on the mast cell grenade we talked about earlier. Without IgE, the mast cell just sits there, even if it is surrounded by pollen.
So if we can block the IgE, we stop the grenade from ever going off. That sounds like the ultimate upstream solution.
That is exactly what a drug called Xolair does. Its generic name is omalizumab. It travels through the blood, finds the IgE, and neutralizes it before it can attach to the mast cells. This is a huge deal for people with severe allergic asthma. If you can keep the IgE levels low, the mast cells stay stable, the leukotrienes never get released, and the asthma symptoms never start. It is like intercepting the message before it reaches the troops.
Daniel mentioned that these upstream drugs are often reserved for severe cases because they are expensive. Why is that? Why can't we just make a cheaper version for everyone? If it works so well, shouldn't it be the first thing we give people?
It comes down to how they are made. These aren't simple chemicals you can synthesize in a traditional lab by mixing powders together. They are biologics. They are literally grown in living cell cultures, often using specially engineered Chinese hamster ovary cells or yeast. The manufacturing process is incredibly complex and expensive. You are basically farming large, complex proteins that have to be folded perfectly to work.
And they can't be taken as a pill, right? I am guessing you can't just swallow a protein like that.
No, because your stomach would just digest them like a piece of steak. They are proteins after all. They have to be injected or infused directly into the bloodstream or the fatty tissue. So you have the high cost of production, the cost of the medical staff to administer the injection, and the fact that these are relatively new, so they are still under patent protection. We are talking about $20,000 to $40,000 a year per patient.
That definitely explains why they aren't the first line of defense. You start with the cheap, effective stuff like inhaled steroids and leukotriene blockers, which cost maybe $50 a month, and you only move to the biologics if those fail. It is a matter of economic triage, as much as medical necessity.
But for those with severe refractory asthma, these drugs have been life-changing. There is another one called Nucala or mepolizumab, which targets interleukin-5. Remember how I said leukotrienes call eosinophils to the lungs? Well, interleukin-5 is the signal that tells the bone marrow to produce more eosinophils and keep them alive. By blocking that signal, you basically starve the inflammation of its soldiers. You aren't just blocking the weapon, you are preventing the army from even being recruited.
It is fascinating to see how specific we can get. We aren't just saying stop the inflammation, we are saying stop this specific signal that produces this specific cell. It is like precision warfare inside the body.
It is precision medicine. And there is even a newer one called Dupixent or dupilumab. This one is really interesting because it blocks the receptors for both interleukin-4 and interleukin-13. These two cytokines are like the dual commanders of the type 2 response. They control everything from IgE production to mucus secretion to the structural changes in the airway. By blocking both, you are essentially shutting down the entire command center for that specific type of inflammation. It has been a game changer not just for asthma, but for eczema and nasal polyps too.
That sounds like exactly what Daniel was asking for, a way to move far enough upstream to stop the whole process. But again, it is an injection, and it is expensive. Is there anything even further upstream than that? Like the very first signal the body sends out when it detects an intruder.
Actually, yes. There is a drug called Tezspire or tezepelumab. It targets something called TSLP, which stands for thymic stromal lymphopoietin. This is what we call an alarmin. It is one of the very first signals released by the lining of the lungs when it is irritated by anything, pollen, smoke, even cold air. Because it is so far upstream, it can work for people who don't have the typical allergic or type 2 asthma. It is like hitting the master kill switch for the entire inflammatory response in the lungs.
That is a great point. It is not just about moving upstream. It is about knowing which stream you are in. Daniel mentioned that not everyone responds to the same treatments. Why is that?
Because not all asthma is the same. This is something we touched on in episode 480 about the mystery of the misguided lung. Some people have asthma that is not driven by this type 2 allergic pathway. They might have what we call non-T2 asthma, which involves different cells like neutrophils. For those patients, these fancy biologics that target interleukin-5 or IgE won't work at all because they are targeting the wrong radio signals. It is like trying to jam a satellite signal with a walkie-talkie.
That is a great point. This is why doctors now look for biomarkers, right? They don't just guess anymore.
Precisely. They check your blood for eosinophil counts or measure the amount of fractional exhaled nitric oxide or FeNO in your breath to see which pathway is active. It is a much more sophisticated approach than just handing someone an albuterol inhaler and hoping for the best. We are moving away from one-size-fits-all medicine.
So, looking back at Daniel's prompt, we have covered why histamine isn't the main player in the lungs. It is just not strong enough to overcome the massive power of leukotrienes. We have looked at why we block the receptors instead of the enzymes, mostly due to side effects and convenience. And we have looked at the high-level biologics that stop the signals before they even reach the mast cells. But what about the future? Daniel works in AI and automation. How is that changing things?
It is changing everything. Progress is being made on making these upstream targets more accessible. There are researchers working on small molecule versions of these biologics. Imagine a drug that could potentially be taken as a pill but still target those specific cytokines like interleukin-5. If they can pull that off, it would be a game changer for people like Daniel who are managing chronic asthma. It would bring the cost down and make the treatment much easier.
Imagine being able to take a pill that tells your immune system to specifically ignore cat dander and pollen while leaving the rest of your defenses intact. That is the dream. No more injections, no more $40,000 bills.
It really is. And we're getting closer. The more we understand about the specific receptors and the structural biology of these cytokines, the better we can design molecules to fit into them. It is a bit like architectural design at a molecular level. We are also seeing AI being used to predict which patients will respond to which drugs. Instead of the trial and error approach we often use today, where you try an inhaler, then try a pill, then try an injection, a doctor might be able to analyze your genetic markers and say, this is the exact molecule you need.
I want to circle back to something Daniel mentioned about his wife Hannah and their son Ezra. When you have a young child, especially one born just last year in 2025, you start thinking about the future of their health. If Ezra ends up having the same allergic tendencies as his dad, the landscape of treatment might look totally different by the time he is an adult.
It definitely will. By the time Ezra is 20, we might have personalized maps of our entire inflammatory system. We might even have gene editing techniques like CRISPR that can tune the immune system sensitivity before the asthma even develops. Instead of treating the symptoms, we might be able to prevent the security team from ever becoming overzealous in the first place.
That is the promise of the technology Daniel works with every day. AI and automation are playing a huge role in this. They are using machine learning to analyze massive data sets of patient responses to these biologics. They can find patterns that human researchers might miss, like why a certain drug works perfectly for one person, but not for another based on their specific environmental triggers combined with their genetics.
It is the perfect marriage of biology and technology. And speaking of technology, Daniel's question about why antihistamines don't play a bigger role actually has a small caveat. While they don't help with the actual asthma attack, many people with asthma also have allergic rhinitis, which is the hay fever stuff. If you don't treat the nose, the inflammation there can actually make the asthma worse. It is called the one airway hypothesis.
So even though the antihistamine isn't stopping the leukotrienes in your lungs, it might be keeping the overall inflammatory load lower by calming down your nose. It is all connected.
If your nose is constantly inflamed and congested, you end up breathing through your mouth. That means you are letting cold, dry, unfiltered air straight into your sensitive lungs. That can trigger an asthma attack all on its own. So even if the mechanisms are different, the systems are linked. You have to treat the whole person, not just the specific organ. The nose is the gatekeeper for the lungs.
That is a great takeaway. It is easy to get hyper-focused on one molecule like a leukotriene and forget that it is all part of one person's experience. Daniel, Hannah, and Ezra are all part of this biological story.
And that is why Daniel's prompt was so good. It forced us to look at the hierarchy of the immune system, from the fast-acting histamine in the nose to the powerful leukotrienes in the lungs, all the way up to the cytokine commanders in the blood. It is a complex, layered defense system that sometimes gets a little too enthusiastic. We are learning how to talk to it, how to calm it down, and how to make sure it only fights the real enemies.
Well, Herman, you have certainly illuminated the why behind the medicine cabinet. I think we have hit the key points Daniel was curious about. We have the potency of leukotrienes, the difficulty of moving upstream without side effects, and the high-tech future of biologics. It is a lot to process, but it makes you realize how much work goes into every single pill or inhaler.
I hope it was helpful for Daniel and for everyone else out there who has ever wondered why their different allergy and asthma meds work the way they do. It is not just random. There is a very deep, albeit frustrating, logic to it all. The more we understand that logic, the better we can navigate the world, whether we are in Jerusalem or anywhere else.
And hey, if you are listening and you found this interesting, we would really appreciate it if you could leave a review on Spotify or Apple Podcasts. It genuinely helps the show reach more curious minds like yours. We are trying to build a community of people who like to ask why about the weird stuff in life.
It really does. We love seeing the show grow and hearing from more of you. If you have a question or a weird prompt of your own, you can always reach us at show@myweirdprompts.com. We read every single one, even the ones that take us a few months to get to.
You can also find all our past episodes, including the ones we mentioned today on Singulair and ADHD, at myweirdprompts.com. We have a full archive and an RSS feed for subscribers. We have covered everything from the chemistry of coffee to the physics of why your shower curtain sticks to your legs.
And don't forget, our show music is generated with Suno, which is a pretty cool piece of tech in its own right. It is a reminder that we are living in the future Daniel is helping to build.
It really is. Well, that is it for today's episode of My Weird Prompts. Thanks for listening, and we will talk to you next time.
See you then. Stay curious and keep those airways clear.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird